Okay, getting into the linear regression, actually, I want to make one last comment before moving into that. And again, just to give help examples. How do you, if you want to do some of these things on your own, where do you come up with the examples? Just as a reminder, of course, you could run these programs. You can get help and pipe it through less or whatever, or you can do that HWeb option that almost every the vast majority of AFNI programs can handle, and that'll open up a web page and you can read the specific examples, or you can actually get into the help output and just search for key terms or whatever have you. And of course, that even applies to something like 3D Deconvolve, for example. And if you notice, there's no, like in 1D Tool, we actually have at the top a table of contents here where we can click on example 6A or whatever. We don't have that for 3D Deconvolve, so you should complain to us lazy developers. We haven't stuck in that. That would take at least 2 or 3 minutes to do so. So anyway, maybe that'll happen before you're actually watching this now. We'll see. At least a 17.39% chance. But getting into the 3D Deconvolve command now, this is at the heart of why we're doing this at all, right? The whole purpose here is for each one of our subjects, we want to generate beta weight maps of effect sizes for our two stimulus conditions of interest. In this case being the visual and audio reliable conditions. So we did a bunch of pre-processing to get the data to a point where we think it is suitable for a regression, and that the output will be, at least to some degree, reasonably comparable across our subjects, and hopefully even across subjects in other studies. So now we actually set up the regression, and again, it's our job now to tell 3D Deconvolve how we want the data to be modeled. And 3D Deconvolve's job is to fit the model to the data as well as possible with a minimum least squares fit to generate the fit time series, to generate beta weights for every regressor, those of interest and those of not. But the baseline terms are not output by default unless you ask for them. And possibly many people will run 3D Remel fit additionally or instead of 3D Deconvolve and get the beta weights from there. But either way, we're running some sort of linear regression model. So let's first of all make sure we understand or we recall and are comfortable with the model that we are using to fit the data. So again, here we've got our 3 runs of data. Notice there's a wildcard here. If you use a wildcard in the input or in whatever file naming scheme you have in the script, you have to use a complete file name. Let me just briefly demo this. If I should set subj equal to ft. Notice I'm in T shell here. If you're in bash, you would type just subj. How do you spell subj? Oh my goodness, equals ft, and you'd be done with it. That's bash syntax, but I'm in T shell, so I type it like this. So if I set that variable here, and I'll just do ls on this, or how about a long listing, so it looks more like a bunch of files. When we apply this with a wildcard, the shell sees this wildcard and it fits it with anything that it can. In this case, there's a 1, a 2, and a 3, and it finds 3 file names. Or you could use just echo just to see what it's expanding to. If we didn't have the head there, we'd get that famous shell command, no match. And it's not a problem with the echo command, just like we mentioned it before, possibly seeing AFNI no match. It's a problem with wildcard matching. In this case, there is a wildcard character in there, and it's not matching any files. but if we put the dot head, it does match. Again, notice you since I keep mentioning the square brackets being wildcard substitution, we can put these here, and oops, I forgot the 0. Those match any single character in the brackets. So I typed a 1 and a 2 in the brackets, and notice it got run 1 and run 2, but not run 3. If I did 1, 2, 3, or if I did, oops, I lost my mouse cursor. If I did 1 dash 3, I think even if I did dot, nope, maybe that depends on the form of matching that I'm using. But at least in any of these cases, the square brackets will fit one of the terms inside, and then you can match it that way. The other wildcard, as long as I'm babbling about it, is the question mark, which will match exactly one character. And for example, if I wanted to match R character, like R01, R02, I could use 3 questions, and that's fine too. Anyway, there you have it. So we've got our 3 data sets input on the command line, and now we start setting up our model. First of all, what we have up here is our sensor file. So we're telling 3D-Convolve to generate a complete regression matrix to match to the data, but then for any time points that are 0 in this sensor file, we're going to remove those time points from the regression. The reason the full model is created first is so that we have time continuity. So, it knows where the run breaks are. It knows for each event how long the stimuli, well, we tell it how long the stimuli last and how long to convolve a model by. For the slow drift fitting, it needs time continuity for that. But once it develops the whole model, then it can remove the time points that we want it to remove. So now things that go into the model. First of all, we have some ortvecs, and that's short for orthogonalization vector, time vector or something. And we're telling it basically to model these things. Run 1, 2, and 3, the motion, d-mean motion parameters. That's the per run motion. We wanted to model these things, but we just wanted to orthogonalize with respect to them, which is another way to say we just want to put them in the baseline. We don't need beta weights for them. We want to model them. We do want to account for their variance, but we don't really care about them in terms of the output. It's just like using a stim file and then saying stim base for those columns. Ortvec is just more convenient. We actually have 6 columns per file, right? Anyway, so that's 18 regressors right there. Then we have polort 3. So that means in each run, we're going to model the slow drifts with a cubic polynomial. So we'll use 4 terms per run, constant, linear, quadratic, and cubic per run. So this is essentially 12 regressors right here. 3 runs times 4 parameters. Then we have 2 regressors of interest that we'll discuss in a moment. And that's our entire model. So not too complicated, the polynomial slow drifts, the motion, the stimuli of interest, and the number of time points in our model will be affected by the sensor. But otherwise, we have 18 plus 12 is 32 regressors here. So 32 regressors in our model, and let's take a look at how it looks. Note down here, our regression matrix is in x.xmat.1d. So let's plot that. 1d plot dash subscale on x.xmat.1d. Blow this up a bit. Maybe I've gotten too tall. So counting from the bottom to the top, at the bottom you see we have the polynomial terms per run. So you see here's the constant, linear, quadratic, and cubic drift terms for run 1, and then they're all constant 0 after that. And then the same 4 terms for run 2, and then the same 4 terms for run 3. Then we have our 2 regressors of interest. And just to, well, I'll come back to how those are constructed, but our 2 regressors of interest. And then we have the motion parameters for run 1, run 2, and run 3. So this is our complete model. We'll use this to fit the data, or 3D deconvolve. We'll use this to fit the data as well as possible and generate our beta weights. So let me leave this up here for a little bit, and let's recall, the polynomials are clear for each run. We just have the polynomials of the respective degree. These, give us 4 regressors per run. And the motion parameters are easy. We have our 6 motion parameters per run, but they're all extended to be 450 time points, zeros outside of the current run. So let's just recall how we generate the regressors of interest. And I've got that running again. I'll leave it running, so I'll do Control Z again and BG again. And we told 3D deconvolve that, for example, we have our 2 stimulus classes of interest, viz and odd, and we told it to model them as using the block function, which is like a 15-second response curve for the impulse response curve, and we want 3D deconvolve to convolve that block curve with a 20-second boxcar curve, and then make the resulting convolved time series of maximum height 1, just so that the regressor is scaled to unit height, and that makes the beta weight that we get as output the convolved percent signal change. Without the comma 1, this would probably convolve this is a unit height by default, and so this would convolve to height like 5.4 or something, and that would inverse scale the beta weights down by that 5.4. This way the beta weights will be the complete percent signal change. So, and just recall now our stimuli of interest are in the stimuli directory, and we can cat those files. So the first 3 lines are for the AV1 viz.txt, and the second 3 lines are AV2 odd.txt. Note that I have a constant that the file names have a constant prefix followed by an index, AV, and then index 1 and 2. And then in the files I have a label after that. So that makes understanding the files very easy. And for example, when you type ls, I meant to do a long listing. When you type ls on the files, that puts them alphabetically according to your index. So then when you're handling them, it's more comfortable to keep them in the order that you want, rather than, for example, in some random order based on the label that you named the file with. Anyway, so we have the visual task and the auditory task, and for example, again, the events in the visual reliable task, in the first run, the first visual reliable task was at time 60, and then there was another visual event at 90, 120, 180, and 240. So just recall from our earlier slides, the experiment design here, we have a 20-second event followed by a 10-second fixation. So here's run 1 with the auditory reliable. Maybe I should cat stim AV2 separately just so you really see it clearly. There's an auditory event at time 0, and then 30, and then the visual, 3 visual events, and then etc. So we are giving 3D deconvolve just onset times, and it's going to use the block function to create the ideal response curve, but then we tell it we want it to consider the events to last for 20 seconds, and we want it, and therefore we want it to convolve the 15-second response curve with the 20-second block curve, 27 boxcar curve, say, which will result in a 35-second stimulus response curve, which is what we see here. These each last about 35 seconds. It doesn't quite return to 0, but it gets pretty close. In case you're curious, we can just look at this. Well, let me plot that again, I'm sorry. So recall we have at the bottom we have 4 by 3 polar terms. So the indices for these columns in the matrix are 0 through 3, and then 4 through 7, and then 8 through 11. So we skipped the first 12, so these are column indices 12 and 13 in a zero-based system. So if we wanted to only plot those regressors of interest, we could plot 12 and 13. And there are the regressors of interest. And now they're a little more clear. We can make them larger. Okay, so that looks good. Where's time point 42 should be. So where you see that, remember we're censoring a little bit here. And if you look at the black curve here, you see it's just shaved off a little bit at the right end here, and that's right around time index 42. That's where we had censoring. If you recall, the 3D Convolve makes a complete regression matrix and then removes censored time points. So that's why there's this additional option, output -x1d uncensored. It can output an X matrix that doesn't have the censoring in case we want to see the complete X matrix. So if I do, well, let's just back up over this and do our no censor one, and then 12 and 13 again, and we'll put in the background. So these are the same regressors, just without censoring for comparison. You notice the top one is a little shorter, doesn't quite get to 450. That's because it's lost a few time points. So the bottom is stretched out a bit. But for example, that first visual event is chopped off here, but it looks more complete in the one without censoring. Anyway, so these are the regressors of interest. A close-up of them. Any questions? No, good. So now that that's our complete model. Now that we understand the complete model, let's just briefly peruse the last options in here. We tell 3D Convolve to use, we give labels for a stimuli of interest. So in the 3D Convolve output, we'll have viz and odd be applied as labels within any volume that pertains to those stimulus conditions. We tell 3D Convolve to use 2 CPUs for the analysis. We give it a couple of GLTs to compute. For example, viz minus odd, a very basic one, and we'll give it a label v minus a, so just the contrast of those two. And a different one that takes their average, half of each of them added together. And we'll call that mean VA. We want fstats output, we want tstats output, we want to name the X matrix like this. We want the JPEG version of the X matrix. Well, I don't really care about that, but that's what we do. We want an uncensored form of the matrix. And then we specify we want the residuals, the error time series -erts, stored in erts.subjectID. And lastly, we give it a prefix for the all the bucket data set that contains all the beta weights and the t-stats and the f-stats and the GLTs and whatnot. So that's the 3D Convolve command. And I don't know if I want to make one little point after this. That's TSNR. Yeah, where's our fit time series? We usually do it here. Oh yeah, there we mention it. Oh, it's not until way down here. The order of these things doesn't matter so much when I'm creating the stuff in AFNI proc, but it just so happens that the fits isn't created until down here. Really, I ought to do that right after 3D deconvolve. But anyway, recall that to save RAM, we had that option. We had that option in AFNI proc to save RAM usage while we run the analysis, and that's regress. Whoops, I did SO3. Oh my goodness. Regress compute fits. So that was just telling it we don't want 3D deconvolve to compute the fit time series. Remember that the residuals, the fits plus the residuals equals the input. So there's no reason to have 3D deconvolve compute both the fits and the erts if we don't want it to. We can just subtract the erts from the original to get the fits. So that saves us like 40% of the RAM usage in 3D deconvolve. So that's why there's no fits option. By default, there is one. And with this option, we're telling AFNI proc not to include the dash fits option. So later on, way down here, I was just doing the searching. We just computed it with 3D calc. We just took the all runs and the erts. A is all runs, B is erts, and our expression is A minus B. So we subtract them to compute the fit. So this is the same result that we would get with 3D deconvolve, but it doesn't make 3D deconvolve use the RAM for that operation. So why don't I leave this off at there, and then we'll come back and we'll look at the 3D deconvolve results and make sure we're happy with what is there. Okay.